Okay, folks. We're right on time, so we'll get started. I'm assuming all of the groups, you should have gotten your draft marked up of your project from me. So if you have questions, you want to set up a meeting and something, I know 3 of the 5 groups have people who TA in one of my classes, so we can visit there next week if need be. The other groups, if you want, we can set up a time to go through things. The other is you should have received the 5 lab reports that you will be then meshing together to put a one final major report together, looking mainly the differences, obviously different variables that each of the groups used, and that will serve as a basis for your final written lab report, but also the basis of your presentation, which I think is on 3rd of May or whatever the last Monday is right before study break starts. So that's the housekeeping that we've got. What I'll be doing today is talking you through what we refer to as refrigeration basics, just to give you a good understanding of how refrigeration, and with refrigeration, obviously freezing. So any of the cold storage types of things that are going on. So you at least know the terminology, the jargon, and so forth. At this point, the way the curriculum's set up, we don't have you doing any calculations and so forth. In a previous life, I used to spend about 2 weeks on this, and we did all kinds of calculations and so forth. But this is really to give you a qualitative understanding of the whole area of refrigeration. Obviously, why is refrigeration or freezing? Why do we give a rip? It slows spoilage, as we well know. Long distance shipping prior to refrigeration. Things couldn't be shipped very far. But all you could do is salt the heck out of it if you wanted to preserve a number of things. You get into long-term storage. Something I'd make sure is as you get into your food careers, long-term storage is wonderful, but long-term storage also means your money's all tied up in inventory. So you want to try to minimize how long, but again, it's a valuable tool. And obviously production of a lot of different dairy products, you know, I guess I'm dairy, but a lot of products, if we didn't have refrigeration, if we didn't have freezing, the ice cream group would not have an ice cream project because there would not be any way to freeze it and so forth. So, but what do all of these have in common? All of these have a basic refrigeration system that is generating the cold air, whether at refrigeration or at freezing temperatures. Basically what happens, and we'll go through, you'll see that you'll get sick of seeing this slide. It's probably there at least 2-3 times yet. We have the warm air that is in the room, in the cooler. That warm air is blown with a fan across an evaporator, and exactly what is occurring is the evaporator is the right term. Your liquid refrigerant or liquid vapor refrigerant, I'll explain why it's vapor in here, but let's say as much liquid as possible flows through the evaporator. The warm air comes in contact with the refrigerant, converts it from liquid to vapor. That vapor then is carried away. It goes through a compressor, because now we have to take that heat out, because this is a closed loop system. We need to remove that heat from the vapor so that we can reuse that refrigerant. So it goes through a compressor and we have a high pressure vapor form. It then goes through a condenser where we're going to apply some type of refrigeration or of cooling, probably in the form of cold water, or in the case of our home freezers and refrigerators, air will remove that heat. You know, you put your hand behind your refrigerator and it's hot. That's because you're removing that heat that was inside, got transferred to the outside. So then it becomes a liquid. That liquid then has to work its way back to the evaporator. And we go through what's called an expansion valve, which will allow that more or less high pressure liquid to flow through. And because you relieve pressure, you do get some vapor, but you'd ideally like to minimize the amount of vapor there because the vapor ain't worth much as far as removing any heat from the system. So when you look at a refrigeration system, it's basically a 5-component system. You have a refrigerant that acts as your transfer media. You have the expansion valve, which allows this refrigerant to flow into the evaporator. Takes up the heat. The vapor then has to be compressed, goes through the compressor, eventually reaching the condenser where we remove the heat and dispel it to the atmosphere. So really what we're thinking is basically all we're doing here, taking the heat out of the room and throwing it outside, if you want to think of it that way. And again, just another picture, a hot air, evaporator, vapor, condense it, or compress it, condense it, expand it, or allow it to flow back into the system. And what we'll do the bulk of the time is kind of walk through, after a little bit more introductory material, we'll walk through some of the variations that you can see mechanically with this system. If some of you are thinking, looks really simple, and I've been in refrigeration rooms and stuff and go, doesn't look that simple. That's because this is just a single system here. If we start to tie these together, especially when we want to get to really low temperatures and have a very large area, one unit just can't do the whole thing. You'll have them worked in tandem, in parallel, in different configurations. If you ever can't get in the door, but you all were down doing the agglomeration lab, that wall just to the north of the agglomerator, that is the wall that goes right around the corner is the door that will get you into the compressor room for basically the pilot plant. Okay. Refrigeration systems, how do we rate them? How do we compare them? You go to buy a car, what are you thinking? Horsepower. Well, with refrigeration, we want to talk about tonnage. And you rate refrigeration systems on how many tons of cooling is it able to deliver in a 24-hour period. So as the definition says, it's the heat removed by conversion of 1 ton of ice to water at 0 C. So basically what we're talking about here is the removal of heat that is then causing the heat of fusion to be lost from the ice so that it turns back to liquid. So this is kind of hard to get your head around, but really what it is in the old days, you took a ton of ice and you put it in your ice chest or in the walls of your building and so forth. And how much tonnage, how much ice you put in there you go, well, I need about 45 tons of ice for the next month in order to keep this or that cold. So basically it says here, the latent heat of fusion for water is about 144 BTUs per pound at 2,000 pounds per ton. Therefore, we're removing 288,000 BTUs. If you want to convert it to kilojoules, which would bring us more in line with the rest of the world, simply do this calculation. And so what we're talking about here is removing 3.516 kilojoules per second. So that's a lot of background, but the main thing for you to think about as a professional, if you're ever in a situation where you're dealing with helping to design a new plant and so forth, and the refrigeration guys start talking tonnage, this is where they're coming from, removing this much heat. But how large a system do you need? That's the question that you'll have to ask. And maybe the other question is, if we want to expand our capacity, the amount of product we're making, and we say, well, we got lots of space in the back of the freezer. Sure, you may have square footage or cubic footage to put those hunks of meat, the ice cream, your frozen peas, whatever it might be. But does your system have the ability to take the heat out? So when you do this, you need to make sure there's a heat analysis done. Probably not what you would do as a food scientist, but you want to make sure that you're asking the right questions so that you don't wind up with the wrong type of system. Like the other day when I was talking about pumps, you want to make sure you got the right horsepower. Well, here you want to make sure you've got the right tonnage as far as heat that you're going to remove. So what do you need to think about? You need to think about, you want to get to what temperature and how are you going to maintain it? You have to think about everything from the specific heat of the product, because a lot of times we're cooling in these freezers and refrigerators. So how much specific heat are we removing? Cooling tunnels or freezing tunnels for things like peas and beans. With a cart and getting everything. So you need to consider the number of people in there. And then obviously things like how good is the insulation? And that's a trade-off you'll need to, especially if you're in the design phase, what trade-off is there between horsepower or refrigerant capacity versus how much insulation do we want? Insulation, you can go, well, we just put all the insulation we can, but at what point are you spending more on the insulation and you'd be better off with a little bit bigger tonnage in your system? How many openings, how many holes? Especially if you're backing semis up to load, to offload things, either in or putting stuff out on them to send away. So you've got openings where you're going to lose heat. Especially if you don't pull the door down before you pull the semi away and it's 95 degrees outside. You just lost a lot of heat there. So you got to think, all those types of terms. Okay, what are some possible refrigerants? So long laundry list here, everything from sulfur dioxide to ammonia, which we'll spend quite a bit of time talking about. You've got difluoromethane or difluoromethanes. We have the freons. The freons are somewhat out of favor, obviously, because of the ozone issues that come into play there. You can literally use carbon dioxide, but again, you're having to take it from vapor to liquid to allow it to go back to vapor. Different other compounds known as zeotropes, azeotropes, and so forth. Actually, in our pilot plant, I think it might be the system we use in there is what's called, we have an R302 refrigerant. Our system broke about 30 years ago, and most of the pilot plant was retrofitted with a new refrigerant, which was better, although we still have ammonia-based system up there, because as we'll see later, you just don't say, let's just change from ammonia to this this is the Wunderkind refrigerant, and it's all these you just don't interchange these because of some issues which we'll talk about in a moment. Basically, this is what's called refrigeration effect. You want to measure the heat taken up by the refrigerant. So when you start talking about a pound of refrigerant A and a pound of refrigerant B, which one takes up more heat? The engineers or the refrigeration people define refrigeration effect as the heat difference between saturated vapor at 5 degrees Fahrenheit and the heat of the liquid at 86 degrees Fahrenheit. Because remember that vapor, you've gone through a phase change, it is taking up a lot of heat. So they measure those, that's sort of to standardize between refrigerant A and B and C and so forth. Now for a comparison, we get some common refrigerants here. What is a refrigeration effect? And defined here as in the BTUs of heat that you're removing per pound of refrigerant. And then the flow for 1 ton of refrigeration. How many pounds per minute have to flow through the system in order to achieve that 288,000 BTU removal over the course of 24 hours? What's the one that jumps out at you right away? Well, I suppose, especially since I highlighted it, bolded it, is ammonia. Look at that refrigeration effect, almost 500 BTUs per pound. Freon 12, very common, still very commonly used in refrigerators, air conditioning units, your car air conditioners, and so forth. Difference there of almost 10-fold, or 9.5-fold if you want to argue semantics. Also notice how little ammonia has to flow versus the amount of freon. And you may think, well, why isn't everything ammonia? It'd be great, except ammonia has a number of issues with it. You have to have a very, very tightly sealed system. Ammonia is it's toxic if you breathe it. Not to scare you too much, but there was a incident, and it's maybe 40 years ago now, at a plant in Minnesota where someone was working on a freezer, and they opened it up, and they thought they had pumped out all the ammonia, took it in the face, and died. Basically, if you breathe ammonia, it'll burn out your lungs, burns out the alveoli. So, ammonia, the nice thing, well, I shouldn't say nice thing. The good thing about ammonia is at least you can smell it. This was one of these where a person went to loose it on and bang, took it right in the face. Okay, pressure ranges, because you remember we're going to be going from vapor to liquid, and all kinds of pressures are being involved in here. Carbon dioxide at 5, it's right around 300 pounds per square inch gauge. When you get to 86, we're over 1,000. So a huge pressure buildup. Think about your pipes, think about your seals. Then you go to ammonia. Ammonia is fairly reasonable. 20 and 155. And really, when you start looking at the size of the molecules, those are very similar molecular weights. Not quite the same, but close. You go to Freon. That's why Freon 12 is one that a lot of people have, historically used for no other reason than you're working under fairly low pressures. You aren't necessarily having, the seals and so forth. Then we have sulfur dioxide. The problem here is you got to have a vacuum on one side, admittedly low pressure on the other. Density, the weight, pounds per square foot, or cubic foot, excuse me. Something that's lighter is probably better just because of the weight in the pipes, those types of things. So you're seeing kind of a trend here. Ammonia is kind of crawling up the ladder as pretty good. So when all is said and done, and you need to compare refrigerants, here's kind of a laundry list of things to think about. What kind of pressure range? A smaller range without high pressures, probably better. Again, keeps seals and stuff good. Obviously, you want as much bang for your buck or refrigeration per pound, so refrigeration effect is a major player. Density, you'd like a little less dense material. Toxicity, something to keep in mind. Of these, if you want to say it, the one that's acutely toxic of that list, the more common ones, is ammonia. You can make the argument that the freons are toxic, but they would be more long-term toxicity, screwing up the atmosphere and so forth. So that gets into safety. One of the things about use of refrigerants, I'm not sure exactly what the laws are in the state of Minnesota, but I know in the state of Wisconsin, any public facility, you can't use ammonia because of the potential for it is explosive and so forth. And the only reason I know this one is when I was a graduate student there at Wisconsin, they had to replace their refrigeration system. Their ammonia system went kaplooey. So as long as you got it, you're grandfathered in. Their problem was, you just, as I mentioned before, you just don't switch from one refrigerant to the other because of, you're probably guessing it, the refrigeration, like how much refrigeration do you get in pounds per square foot and so forth. You're thinking, yeah, ammonia doesn't, you can have a little bitty pipe and that ammonia do a lot of cooling for you. They literally the university had to get a special dispensation approved by the Wisconsin legislature to allow them to replace their ammonia system. If they were building a plant, you can use it in a processing plant, but that's not a public facility. So like if we were trying to refrigerate this in I guess Minnesota, we don't have that because we were allowed to replace our ammonia system when we broke down back in the 80s. But again, we replaced just a small portion. We actually, as we bought new equipment, we switched over to a different cooling system. Our freezers upstairs, our walk-in freezers and so forth, are not on an ammonia system. They're on the R502 system. So obviously leakage comes into play, how well or something doesn't leak, and how do you detect leaks? So you really need to be thinking about those types of things. So that brings us back to your favorite picture from this slide set. And what we're going to do now is talk a little bit about what occurs with some of the pressures and so forth going through here. And then the bulk of the time we'll spend that's left today talking you through what are some of the variations that you can have on each one of these pieces of hardware as they go into your system. This is just a schematic of the impact of temperature on the specific entropy of the system, the variability, the randomness that's going on in there. What you need to take a look at here is just kind of what happens as we flow through the system. So if we start down here at number 5 on the lower, I guess that's right-hand side, we have just gone through our expansion valve and we have our liquid vapor that is flowing, that bottom arrow flowing through the evaporator, taking up heat. So we're now at the coolest point. Then we have our saturated vapor. And again, the entropy, very random arrangement here because it's vapor. We go through the compressor and we go from a saturated vapor to a superheated vapor as we push it together. Then sweeping across the top up here, we will go through the condenser and we're able to remove that heat. Now we're back to a saturated liquid. So we picked up the heat down here at the bottom in the form of the vapor, taken that heat, and we'll talk about what we do with that heat later in the different types of condensers. But basically, we've transported the heat from inside our room to some external location. So again, we've talked enough about refrigerants, but now we'll talk a little bit about the other elements that can go in the system. The expansion valve, the place where that liquid goes or is allowed to start its path into the evaporator. Very simplistic way of doing it. You walk up and you turn the knob. Not a very efficient way of doing it, unless the labor is really cheap and you can have somebody stand there and open and close the valve all the time. But allowing that high pressure liquid flows in, and as you release and open and allow it to flow into the pipe, into the evaporator, it's under less confined space. So therefore you get some of it being converted to gas. You'd like it to stay as much as possible in the liquid state, because going from liquid to vapor is going to take more heat, even though you're just like the heat of fusion, you're removing that heat of vaporization. You'd like it to mostly be going there, because any heat that goes and becomes associated with the vapor is just sensible heat. You're losing some of your refrigeration effect at this point. Systems such as what we have up in the pilot plant use these various float systems. So basically the liquid, high pressure liquid, is coming to the back of the chamber. You've got a float in there. You're allowing your liquid to go to the evaporator. And as soon as it reaches a certain level, it's just opening and closing by itself. That is more of a low pressure system. The high pressure system here, we're keeping the liquid more or less as liquid. It's under pressure, so we aren't getting that conversion from liquid to vapor, which we're getting some up in the other portion. There are automatic systems that are available, so you don't have the float systems. Again, sensing the pressure in the evaporator, is there's less pressure there. It's saying, well, the vapor, the liquid's been converted, so it's flowing out. It allows more of the liquid to flow in and remove the heat. Some are set up thermostatically. Basically, you're sensing the temperature of your liquid as it flows, or your vapor as it flows out, and allows more or less in to the system, kind of like setting the dial on your refrigerator. So a lot of different ways of basically taking liquid and allowing it to get to a point where it can take up the heat from the room in the evaporator. Now, a few configurations on evaporators. If any of you, if you think about it, you've probably all at some point walked into one of either the walk-in coolers or walk-in freezers in the pilot plant. When you walk in the door, somewhere up in the corner, you're going to see a big box. And that big box is the evaporator. That is where the liquid is being converted to gas and taking the heat out. And if you do something, be careful if you do this, put your hand up behind the evaporator, you'll feel the hot air. The reason I say be careful, because there's a fan blade up there and they're not necessarily covered. So you don't want to lose your fingers. And then you put your hand out in front. You can feel that difference in the temperature. You're blowing that cold air out. With evaporators, there's two approaches that can be utilized, a direct and an indirect approach. And we'll talk about the direct first and then what would be an indirect approach, which is commonly used in a lot of different industries. Configurations, you can have a bare pipe that you're just blowing the liquid's flowing through, you're blowing on it. You can have the fin tube. You can use plates. This is just the example of the pipe. You've got a direct expansion down there. You're opening it up. Your liquid gas is going through. And all that's really occurring in your room is the hot air is blowing across the pipe, cooling it down. And that's where your heat exchange is. Your heat exchange is from the air hitting the pipe and then removing the heat and going into, very similar to what you do if you use a tubular heat exchanger. Then we have a flooded system. In this case, you have the liquid flowing through the bare pipe. Some of it's converted to vapor. That vapor is then sucked off and goes back to the compressor, whereas the rest of it, liquid stays there. So you aren't pumping liquid through and just wasting it, so to speak. You can take the bare pipe. It's again looking at different configurations. The bare pipe, then you have the fin tube where you literally have the tube floated through the fins. The benefit here is you've got more surface area. Same with the plates. Some of you recognize the fin tube. Back of your refrigerator. You got all that little grating there, and that's what you're doing. So those are direct. Now indirect. And what occurs in an indirect is you're utilizing that refrigeration system just as I described it. You've got the vapor going in. You've got, in the case of an ice builder, that vapor is going through a pipe. As it goes through the pipe, you've got water around the outside. And what happens? Water freezes. Just like what happens in this winter time when you go out to your car and you're huffing and puffing, scraping the ice, and you go, and you keep building up a fine coat of ice. Well, what's happening what you do in the ice builder is you literally have a big box with a huge number of pipes in there that you have the refrigerant flowing through, and you build up ice around the pipe. Let's say the pipe is 2-inch in diameter. It might be a 12-inch diameter mass when you have the ice built on it. And then what do? You pump water from the ice builder into wherever you want to cool. The dairy plant that I worked in, that was how we did our cooling at the pasteurizer. And if you think about a plate pasteurizer in the cooling section, be really tough to squeeze that sucker tight enough to have refrigerant in there. So it's much safer to create ice. And we do have an old ice builder down in the basement. Build ice, make ice, pump the water up, cools down your milk, put it back in the ice builder and let it cool. So you're indirectly refurbishing. Very safe from the perspective that you don't have especially if you're using ammonia floating around in the processing area where there's a lot of people. I shouldn't say floating around, in vessels there where there's potential for leaks. You can use a brine system. Basically, it's an ice builder where you don't have just water, you have salt water. The idea being you're able to drop the temperature a little bit more before it freezes. So the water that you're bringing off an ice builder at coldest 32 degrees Fahrenheit. Brine system, you can get it down around 20. And some of the older ice cream freezers, the brine system was how they refrigerated. They pumped this brine water through there. Problem with brine systems, obviously, corrosion. You put saturated, salt systems, it's not the best. You can use glycol, chemical refrigerant, and a lot of people, this is something they will use in heat exchangers. Let's say when you're receiving your milk at your dairy plant, you may not want to have ammonia, but you want it cold. So you could utilize glycol, where you're pumping glycol through a glycol tank. It has tubes just like the ice builder, but instead of potable water, salt water, you now have the brine in there, excuse me, the glycol in the system. The compressor, what are we going to do here? We're going to take that vapor and start to bring it back around to a liquid for us. A lot of different compressor types. Basically, what type of pump are you using? Reciprocating, centrifugal, rotary, anything that will take that liquid, or excuse me, that vapor, squeeze it back down to a high pressure vapor, which we then will later remove the heat from. Some of the factors that will affect performance here and what you would need to think about when you're saying which one of those do we use? The revolutions per minute, what refrigerant are we using? The suction pressure, how much suction pressure do we need? What is the discharge pressure that is being generated? Again, all of this, maybe things you just kind of file away so that you can talk smart when you're, or listen smart when you're talking with your refrigeration engineer. This is the type of compressor that we actually, if you go out the back of the pilot plant, there's a cooler there, but there's also just to the, I guess it'd be to your left, the right-hand side, there's a small utility room, and that's where the compressors are for the coolers that are back there. The storage cooler for the pilot plant, as well as the one that they have the brine tank in, not for refrigeration, but for soaking cheeses that you're going to brine. So you have basically an electric motor. You've got the compressor in there, probably a piston type compressor, squeezing down that vapor to liquid. And then you have an evaporator coil there, which is basically different from the one we had before, but we're releasing that heat as we try to condense down that vapor, or that high pressure vapor. Again, just the type of thing, operation of a cylinder, similar to what we talked about in a pump. It's a piston pump is what it is. Example of what happens with the pressure. Again, the volume that you have going in, you compress it down at D, then it's higher pressure and back and forth as you go along. Okay, the condenser. Basically, we're now down to the last piece, right? Yeah, a couple of the look. The reason I'm laughing is the couple people in the room here, and they saw this, and I think it was one of those, everything else looked like little bitty, not too complicated. Now this is a big, well, you got a lot of heat you got to get rid of. So basically what occurs in here is we have our hot gas under pressure coming in on the left-hand side here. It is then going through, it's just a reverse of what went on in the evaporator. This hot, high pressure gas is flowing through some thin tubes, which we have water being sprinkled on. We have air blowing on it, converting that high pressure vapor back to liquid. And then we're exhausting very moist air. And so one of the things you have to be conscious of with this from a safety standpoint, if you've ever heard, I think it was Legionnaire's disease, when a lot of people got sick years ago at an American Legion convention in Philadelphia, where they traced it back to was the condenser system on the roof of the hotel. They had water puddling there from this moist, hot air coming out. The bacteria were growing away. And then the inlet, air inlet into the hotel was not, so you say, it was in a strategic bad place. So they started sucking that air right back in. This is an aside, but one thing to think about when you're dealing with exhausting air from a building and bringing air into a building, making sure where your intake air inlet is placed relative to other things. This food science nutrition building, let's put it this way. You know where the major air intake is in this building? Anyone know? Next time you're here and you walk out the front of the building and you start walking up the hill, you see the loading dock. Look right above the loading dock. That's why it says shut your truck off because it's right by the air intake for the building. Who came up with that design? I don't know, but that's just the way things are set up. I can remember being in a meeting in the conference room down here and we got gassed out. It was colder than heck out and the guy didn't want to shut his diesel off. And so we had to evacuate the building. So it's something to always kind of keep in mind. Where is the air intake? Where is the air outlets and so forth? So it's aside from here, but it's the same type of concept. What could happen with that moist air coming off? A few other ways that you can do it. It's rather than that very big complicated one. Now you're thinking, these make a little more sense. Basically, you have water flowing, being sprinkled in, a series of tubes in here that have your refrigerant and you're removing the heat. So then you're going from colder water to warmer water. A lot of places, what will happen, that water then gets put into a holding pond and they may recycle that water and let nature remove that heat into the atmosphere, especially in a colder climate. Someplace that's really warm, it may not be the best, but cold climate, because if you do go by some processing plants, you'll see ponds of water next to them in the dead of winter and they aren't froze. That's because they're utilizing that water as part of their system. You can also use, very similar to the tubular heat exchanger that you guys did labs with first semester when you were in food engineering. Basically, again, using a tubular type system, flowing water through on one side of the tube, gas through on the other side, and out comes your liquid refrigerant. So the hot gas in, liquid refrigerant out, colder water going in, hotter water going out. So just very simple tubular heat exchanger. And one that you're probably a little more familiar with, back of your refrigerator, potentially what you might be seeing outside when you get your air conditioners going in the summer months here. Again, in this case, you've got a plate and a tube and fin condenser. And what we're doing here is you're allowing air, maybe with a fan assist, blow across. That air picks up the heat. Again, you're bringing it from colder air on the floor, hotter air at the ceiling, and converting, in most cases, the Freon or the like an R502 or something that might be in a refrigerator, in your freezer, converting it back again, vapor to liquid. And so that's the wonderful world of components. The 5-component system again, the refrigerant that acts as our transfer media, the evaporator where we do the work in the room of cooling the air down, either freezing or refrigeration temperature, taking this vapor that is created of the refrigerant, having this process of converting it back, first compressing it down from really volume reduction is what we're doing in the compressor, compressing it down. And that's why with a refrigerant, you would like a refrigerant that carries a lot of, and ammonia is a good one, a lot of heat for the amount of volume, the amount of gas that's going through. You go from vapor to vapor, low pressure to higher pressure. The higher pressure vapor goes through the condenser, which is where we're going to give up the heat and literally condense the vapor back to liquid. Liquid flows to the expansion valve, and away you go. Now, one thing to think about, because I've been known to ask a question on the on the take-home final, why can't you just go from Freon to ammonia in here, or ammonia to Freon? It's all sized, right? The amount of volume that will go from liquid to liquid vapor and eventually to vapor in the evaporator. It's going to depend on the pipe, how much the flow is through there. The compressor, how much vapor can that compressor handle in a given amount of time? Then you get over to the condenser. And if you've got a lot of, I would call it low heat removal vapor versus a lot of high heat removal vapor, it'll be different amount that'll flow through. So you have to, and that's why we couldn't just go, we'll just change from one refrigerant to another. It just didn't work that way. Enough on the cold side of life. Now we'll touch a little bit on boilers, how we're going to get our heat generated. And basically there are sort of two general types of boilers. This is what's called a fire tube boiler. If you look, we've got our fossil fuel down there, coal and so forth. Think of the old train engine, the guys shoveling coal, throwing wood in. What are they doing? They're creating a lot of hot air. That hot air is then going to flow through a pipe, the fire tube. So the tubes are going through a tank of water. The heat from that hot gas is being given up to the water, converting that water first from cool water to warm water to hot water, and under the right configuration, converting it from the liquid state to the vapor state and giving us steam. And then we can pump that steam in our plants through the piping and so forth. Same as people who have a boiler system in a home, the older homes. Literally, this is what you're doing. My grandmother and grandfather had coal. They had to shovel coal in, it would produce steam, and they had steam heat in their house. The flip side of the fire tube is basically the water tube type of system. And in this case, think of a giant Bunsen burner. What we have in the middle there, we have a nozzle down here on sort of the lower right-hand corner, a burner nozzle. Think of it as a big Bunsen burner. It's blowing all this hot air up through a series of, there's a number of tubes there. What's in the tubes? Water. Water comes in liquid, put enough heat into it, water goes out as vapor. Part of this, in order to generate this, obviously there's a lot of engineering that will go into making sure, the pressures and so forth. Because otherwise, if you had one great big open exit, you just have hot water flying out. But if you build up enough heat in that water, it's going to start to boil, convert it to gas, remove that gas. And with that, we have gone through the wonderful world of refrigerants and boilers. And hopefully you guys have a good weekend. And it's on Monday. Kumar will be with you for doing some lecture material, and I will be back again Wednesday and Friday dealing with water treatment and sewage treatment and so forth. And remember, a week from Monday is your project presentations, and 2 weeks is the lab presentation. So again, we'll talk a little bit more about that next week, but really targeting, especially on your projects, you want to give people a good feel for how these products are made. And so when you get to your lab presentations, don't spend huge amounts of time on all the methodology, just what was different from all the different treatments. Because all of you did the labs or saw the videos on the labs. So you don't need to get into all the little nuances of the microfluidizer and so forth. But what happened with different components that you may have put in there. So with that, again, have a good weekend, and see you guys later.